Hi guys, this is Acid Base107. This is part 3 of 4. We are working our way through this, and this is a titration example where we have a strong base and a weak acid. So the strong base in this case is sodium hydroxide, and the weak acid is acetic acid, CH3COOH. Okay, so here's the prompt. A 0.02 molar solution of acetic acid, 150 milliliters of it, with a Ka of 1.8 times 10 to the minus 5 is down here. It's titrated with 0.02 molar sodium hydroxide, which is up here, and we're asked to find the pH after each of these volumes of NaOH have been added. So in A, we have 0 milliliters of sodium hydroxide have been added. So we want to know, we're asked for here, what's the initial pH of the solution of acetic acid. So since no sodium hydroxide has been added, there's no neutralization reaction that we have to write. All we have to do is figure out, based on the initial concentration, which is 0.02 molar of the acetic acid, what's going to be the pH. So the relevant equilibrium equation is going to be acetic acid interacting with water. Okay, so you're going to have this CH3COOH, that'll be aqueous, plus H2O liquid in equilibrium with CH3COO, oh, dang it, there's not to be a third O there, minus, so that's the acetate ion. And so this hydrogen right here is going to jump ship and go over to the water. That's also aqueous. And it's the concentration of this ion here that is going to give us a pH. So down the left-hand side, we're going to write our ice table. Our initial concentration of the acetic acid, we're told in the problem, is 0.0200. So you'll notice with these ice tables that I'm using concentrations and not moles. And when we get to these guys, we're going to use both the BCA and the ice table. Okay, so 0.0200. We don't care about water. And these guys are going to start at 0. And then our acetic acid, once an equilibrium is established, will have lost a certain amount of this acetic acid to this reaction. So we'll lose X here, we'll gain X here, gain X here. 0.0200 minus X. This is going to be X and X. Excuse me. And we are going to estimate the X out because the Ka is small. So what we're going to end up with, I'm going to write it over here, is X squared, these guys, divided by the initial concentration, 0.0200, is equal to our Ka, which is 1.8 times 10 to the minus 5. Okay, a little bit of baby algebra. And square root that guy. Okay, so we get X equal to 6.0 times 10 to the minus 4. And that's equal to the concentration of the hydronium ion. So what we're going to do is negative log X, and that's going to give us our pH. So negative log, second answer. And so our initial pH comes out to be 3.2. Okay, so pretty acidic. Not as acidic as our strong acid in example number 1, but still very acidic. Okay, so that's our initial pH. You just have an weak acid equilibrium to start with. Okay, so now 80 milliliters of sodium hydroxide have been added. So you have 2 phases to questions like this. You're going to do the neutralization part of it, and then there will be an equilibrium in place. So So I'm going to split this in half. And we're going to start out with a neutralization reaction, which is going to be our acetic acid. And we're going to add sodium hydroxide. The sodium is just a spectator here, so we're just going to add the hydroxide. And this is a strong base, so this is going to be a one direction thing. And this hydrogen right here is going to jump ship onto the hydroxide, give us water, and the acetate ion, COO minus, like that. Okay, so down the left-hand side, we're going to do some stoichiometry here, BCA. Remember, this is in moles. So we need to find the moles of CH3COOH at the initial, and the moles of the sodium hydroxide initial. Find the change and see what's there after. We don't care about water. And this guy's going to start at 0. Here, we're going to do molarity times liters. So we have 0.02. And that's going to be times 0.150 because it's 150 milliliters. And we get our initial moles of acetic acid are 0.003. And we are adding 80 milliliters of 0.02 molar NaOH. So we'll have 0.02 times 0.08. And you get 0.0016. Okay, and you can see that there's more acid than there is base. So we're going to subtract the base number. We always subtract the smaller of the two. And that ends us with 0 here. And over here, we're going to add 0.0016 because if we lost 0.0016 over here, we're going to gain it here. And 0.003 minus 0.0016. So this comes out to be left over 0.0014, and this comes out to be 0.0016. So those are the moles left over. Now what we need to do is figure out if we have an equilibrium in which we have these moles in certain concentrations, what is that going to give us for a concentration of the hydronium ion? Okay, so what's left over in solution is a little bit of weak acid and a little bit of its conjugate base. So we're going to divide both of these numbers by the total number of milliliters. So we started with 150 milliliters of acid and we added 80 milliliters of base. So that becomes 230 milliliters or 0.230 liters. And so we get 0.00609 molar, and that's in the acid. And then this comes out to be 0.00696 molar in its conjugate base. Okay, so now we have oops, this should be an H right here. Now we have two substances that are related to each other, and there's going to be an equilibrium in place. So this information is going to then go over here into an equilibrium table. CH3COOH plus H2O in equilibrium with CH3COO minus plus H3O plus. Okay, because if they are left in water, the acetic acid is going to react with the water to make the acetate ion and the H3O plus. So these numbers are going to be translated up into our ice table. And remember, with ice tables, you always use concentration. With BCA, you use moles. BCA is stoichiometry. ice is equilibrium. Okay, so we have 0.00609. We don't care about water. And then instead of being a 0 for the acetate ion, we're going to put in 0.00696. Excuse me. Okay, so in this equilibrium, Le Chatelier's principle says that we will shift to the right and make some H3O plus, because there's a hole there. So we're going to lose X here. We're going to gain X here, gain X here. We end up with 0.00609 minus X, 0.00696 plus X, and X. Okay, this equilibrium is governed by the Ka, which is 1.8 times 10 to the minus 5. And since it's small enough, we can estimate the X out of these. Okay, so what we end up with for our Ka expression is 1.8 times 10 to the minus 5 is equal to this guy's concentration, which we are going to estimate to be 696, times this guy's concentration, the hydronium, which is X, over the acetic acid's concentration, which we're estimating to be 0.00609. Okay, so we're going to do a little bit of baby algebra. 1.8 times 10 to the minus 5 times 0.00609 divided by 0.00696. All right, so when we solve this, we get X equal to 1.6 times 10 to the minus 5, and that's equal to the concentration of the hydronium ion. And we know if we negative log this, we get pH, so we get pH equals 4.8. Okay, so let's check in and see if that makes sense. We started with a pH of 3.2, we add a little bit of sodium hydroxide, and we end up with a pH slightly higher. So that makes sense. Okay, so that's fun. Yay. Okay, let's keep on moving here. Our next one is 150 milliliters of sodium hydroxide. This is going to be in 2 stages. We still have a neutralization reaction to deal with. So we have CH3COOH plus the hydroxide makes CH3COO minus plus H2O. And we're going to have our BCA table here. We know the initial moles of acetic acid is 0.003. And we want to know what is the concentration, or sorry, what's the moles of the sodium hydroxide. So the moles of sodium hydroxide are going to come from the volume of the sodium hydroxide times its concentration. So 0.150 times 0.02, ooh, and that comes out to be 0.003. So this is a significant time in the titration where the moles of acid are equal to the moles of base. So we want to make note that this is an equivalence point. So we're going to lose this, and we're going to gain, oh, this guy's 0, and we're going to gain 0.003 here. And this will be 0, this will be 0, and this is 0.003 there for moles left over in solution. So the only thing that's left floating around in the solution at the equivalence point is the produced conjugate base, okay? So we are going to find out what's the concentration, because the moles aren't going to help us in an equilibrium. We have 150 milliliters of acetic acid. We've added 150 milliliters of sodium hydroxide. So overall, that is 300 milliliters, or 0.3 liters. So 0.003 divided by 0.3. And so our concentration comes out to be 0.01, equals the concentration of the acetate ion. Okay, so if we have a solution that is 0.01 molar in the acetate ion is the conjugate base of a weak acid and will take hydrogens from water. So over here, we're going to write an equilibrium that in which the acetate ion is reacting with water. So we'll have CH3, COO minus, plus water, oops, in equilibrium, and it's going to take a hydrogen from water to give us acetic acid, sorry, I'm starting to stumble here, CH3, COOH, and then we would be left over with hydroxide, which would determine the pH. Okay, so I'm going to go over this right here because I ran out of space. And this water we don't care about. And our initial concentration of the acetic acid is going to come from what's left over after the titration has occurred. So we have this as 0.01. These guys are both 0. We're going to lose X here, gain X, gain X. We get 0.01 minus X, X, and X. Okay? Now, this is the acetic acid's conjugate base acting as a base in water. So what we need is the Kb for the acetate ion. So we know Kb times Ka is equal to Kw. And the Kb is our unknown. Ka is 1.8 times 10 to the minus 5. And our Kw is 1 times 10 to the minus 14 always. Okay, and we get 5.6 times 10 to the minus 10 equals the Kb. Very small, which means that we can estimate this X out. We're going to have to move this question to the next page. Okay, so our expression is going to be 5.6 times 10 to the minus 10, and that's equal to X squared over this concentration, 0.01, and we estimated the X out there. Okay, so we're going to solve for X squared, or solve for X. So we have 5.6 second E negative 10 times 0.01, take the square root, and we get X equal to 2.4 times 10 to the minus 6 molar. And let's see, what is X under here? It's under the hydroxide ion concentration. So if we negative log that, equals our POH, and we get 5.6, and therefore pH is equal to 8.4. Okay, so this is an example of a weak acid, strong base titration question at the equivalence point. We notice this because they're the same number in moles. We solved for what's left over in solution and concentration, and then this ion here has a little side action with water, which changes the pH of the solution. It's acting as a base, so we had to solve for its Kb. And then when we negative log, we end up with POH, and then our pH is 8.4. Okay, we're gonna push through and do part D on our next page here. So you can see in part D, we had 160 milliliters of sodium hydroxide added. And just for the record, we have that added to 150 milliliters of 0.0200 molar acetic acid. Okay, so we have two parts to this question. We're going to have a neutralization part and a what's left over part. So our neutralization is going to be, of course, the acetic acid, which is CH3COOH, plus the hydroxide, and that's going to give us water and the acetate ion. Okay, so this is a BCA table. The molarity times the liters of the acetic acid is, before is 0.003. That's been established in the other problems. And then we have 160 milliliters of our sodium hydroxide, whose concentration is 0.02 molar. So we're going to have, for this guy's moles, we're going to have 0.160 times 0.02. And we get 0.0032 moles there. And so we're going to lose 0.003, 0.003, gain 0.003. And this guy goes to 0, and this is 0.0002 moles of hydroxide left over in solution. So this is an example of where we've gone beyond the equivalence point. Okay, so the pH is mostly affected by this strong base that's left over in solution. Will affect pH more than any equilibrium possible with the CH3COO minus. Okay, so these moles of strong base are going to be the basis for finding the pH, what's left over. So we have 0.002 moles of hydroxide, and we have a total number of liters of 310 liters. So we're going to divide that by 0.310. 0.0002 divided by, and I'm recording 0.310. So we get equal to 6.5 times 10 to the minus 4 molar in hydroxide. Okay, so we're just going to negative log that guy and treat it as if it's a solution of hydroxide only. So negative log, second answer, close brackets, enter. So our POH is equal to 3.2, and therefore our pH is equal to 10.8. All right, so you can see the pH rose as we went up. General forms of pH curves as NaOH is added. Are you okay? As the NaOH is added to a weak acid solution, if this is pH, down here is 1, up here is 14, here's neutral at 7, we see a curve kind of like this, where here's the initial, right here between here and here. This would be our equivalence point. And here would be before equivalence. And here would be after the equivalence, or beyond the equivalence point. Okay, so at the initial, all we did was an ice table. Before the equivalence, we did a BCA, then an ice table. At the equivalence, we did BCA, and we did ice with the KB. And beyond the equivalence point, we did a BCA, and then we negative log the concentration of the leftover. So that's kind of like a generalized summary of what we do.
Inside the garage?
Yeah.
Can I have this?
No. Put some clothes on.
Huh?
Put some clothes on.
Yeah.
That's kind of a generalized form of what you do for a weak acid, strong base titration. Okay, so in part 4, we're going to come back with a weak base, strong acid titration. It's going to be super fun. It might go a little faster because this was an initial teaching moment. Okay, thank you.